Today's lecture is going to be a second lecture on the topic of bandits. So broadly speaking, we're going to continue where we left off the last time, but let me give you first an overview about what the topics are that we're going to talk about. Okay, so we're going to start with UCB, the upper confidence bound algorithm. And in the last lecture, I informally showed you how this algorithm works. And so today we're going to be a lot more precise. So we're going to be more formal in defining what the upper confidence bounds are, and also how we're going to talk in some more detail about how this algorithm works, some motivation for why this should work. Okay, and then we're going to start to consider regret analysis. Okay, so we're going to state and sort of discuss some regret bounds or regret upper bounds for the UCB algorithm, and also for explore then commit, which was the algorithm that we talked about last time. And this will sort of show you why UCB is a better algorithm overall than explore then commit. Okay. And then after comparing these two algorithms, we're going to move over, we're going to consider another algorithm for bandits called Thompson sampling. Okay, and so this algorithm is a Bayesian algorithm, whereas previously both upper confidence bounds and explore and commit were both frequentist in nature. Okay, so the setup is still the same, exactly the same, but Thompson sampling is sort of motivated from using Bayesian principles. Okay, so we're going to introduce this algorithm, and then after that, we're going to do a comparison of UCB and Thompson sampling. Okay, and we're going to sort of see that the performance of both algorithms is kind of comparable, but each one has its own advantages and disadvantages. Okay, and then finally, after we've done these comparisons, we're going to take a step back and think about bandits in larger contexts. Okay, and so essentially what we've discussed so far and what we will discuss until this point and the lecture is a special case, or maybe not a special case, but a certain type of bandit problem called stochastic multi-armed bandits. Okay, so it's not the only type of bandit problem. Okay, so researchers have generalized this to a slightly to a broader class of problems. And so I want to sort of give you a very high level overview about these. And this will tie into a later discussion about modeling assumptions. Okay. So if you want to use the bandit framework to describe the real world, we have to check the assumptions that we're making. Okay. So we have to think about whether this bandits framework is a good model for the phenomenon that we want to study. And if it's not, then perhaps we want to change the framework a little bit and maybe adopt one of these other bandit problems. Let's now talk about the upper confidence bound algorithm. The basic principle which motivates this algorithm is that of optimism in the face of uncertainty. And this means that whenever you have to make a decision, you make it under the assumption that the environment is as nice as is plausibly possible. Okay, and in the context of bandits, this means that we use an optimistic estimate of the mean for each arm. And in so doing, this would encourage us to do more exploration. Okay, wherever the exploration is warranted. All right, so the problem with explore and commit is that we don't explore enough. And so this helps to get around that problem. Okay. So now we're going to be even more formal, and we're going to define the upper confidence bound for each arm, given the data that we have as follows. Okay, so this is denoted UCB, and then, okay, so the two parameters here. So there's the time t. So this means for every t number of rounds, we have a UCB for some arm, and then we have some confidence level delta. Okay, and this is going to be, we're going to have one upper confidence bound for every arm. And how is this defined? Okay, so if the arm has not been put so far, meaning that we have no information at all about it, then the UCB is going to be infinity. Okay, so recall that T sub A, or T is the number of times arm A has been put in the first T rounds. And then, otherwise, if arm A has already been put, then the UCB is going to be the observed mean reward for that arm plus this bonus. And the bonus is going to be 2 times log 1 over delta times this divided by the number of times the arm has been put, and then we take the square roots. Okay, and so this bonus here is called the exploration bonus. All right, so this is the sense in which we are trying to be optimistic. And now the UCB algorithm is defined as follows. Okay, so in round T, we want to select the arm AT as follows. Okay, so in the first K rounds, okay, if the K arms, we're going to select arm T. Okay, so we're going to start by pulling each arm at least once, or exactly once rather. And then for every subsequent round, we're just going to pull the arm that has the highest upper confidence bounds. Okay, and we're going to allow our confidence threshold to vary according to the round. Okay, so let me move this a little bit. Okay, so this is why we use delta t and not a fixed delta. Okay, so that's the UCB algorithm. Okay, so it's pretty easy to state, it's pretty intuitive. And now, let me say a few words about why this is a good idea. Okay, so when do you want to pull an arm? Okay, so you want to pull an arm if it could be the case that the reward for the arm is the mean reward for the arm is high or is the highest. Okay, so you have to act on what you know at the moment. So if the observed mean is high, right? So this is a really good thing. And so this means that the arm is pretty promising. And on the other hand, if the observed mean is not so high, but we have not put the arm too many times before, right? So, and then in that case, this observation that the mean of the arm is small could just be because of bad luck, right? Because we got unlucky in the first few pulls. In that case, if you put the arm only a few times, we also want to try to explore it more. Okay, so if either mu hat of A is small, so mu hat of A is big, or T sub A of T is small, then we should want to, this should incentivize us to pull arm A even more. Okay, you can see that both of these appear inside the formula for the upper confidence bound. Okay, so mu hat of A is the first term, and T sub A of T is in the denominator for the second term. Okay, so intuitively, this sort of makes sense. But we want to go one step further and explain why the exploration bonus has this exact form. Okay, so why is it square root of 2 times log 1 over delta divided by T sub A of T? Okay, and the reason why it has this exact form is because we want this bonus to reflect our confidence level about the true mean for this arm. Okay, so the bonus should be based upon confidence intervals or the length of confidence intervals. Okay, so now let's do some revision about the content that we learned in the lecture on concentration inequalities. Okay, so recall that if y1, 2, yq are independent, one sub-Gaussian random variables, then okay, we have this formula, or we have this bound. Okay, so the probability that mu is bigger than the average of these yi's plus this term, 2 times log 1 over delta divided by k. Okay, so this is going to be less than delta. Okay, so this is something that we get from Hoeffding's inequality. After, so Hoeffding's inequality starts with replacing this by t. And over here, we have exponential minus t squared divided by 2 times the sub-Gaussian parameter sigma squared in the denominator here. Okay, but that parameter is 1 over root k. Okay, so square of that is going to be just k in the numerator. And now we set this to be delta, and then we solve for t, and then t turns out to be this expression that we have here. Okay, so the upshot of that is that if you set UCB to be something that looks like this, right? So UCB of t is equal to the mean at that point plus 2 times log 1 over delta times t to t, then we should expect that the probability that the mean for arm A being bigger than our upper confidence bounds okay, so this should be less than delta. So that's what we should expect based on Hoeffding's inequality. Okay, so this is actually not true because of a technicality. Okay, and that is because whenever we take this average, okay, the number of rewards that we've seen so far, T sub A of t, okay, so this is not independent of the observed rewards. For that arm, okay. And this lack of independence is going to make our life a little bit hard. So it's going to make it that this does not actually hold. Okay, but still the intuition is broadly correct, and we can try to fix this a little bit by inflating the log numerator term by just a little bit. Okay, but this is the whole reason why the UCB formula has this form. So here is a theorem that gives us a regret bound for UCB. Okay, so here we want to set the confidence level for round t should be equal to 1 over t cubed. Then with this choice, the regret for UCB satisfies the bounds 3 times sum over all the arms of the suboptimality gaps plus the second term, which is the sum over all the arms for which are suboptimal. Okay, so the suboptimality gap is bigger than 0 times 24 log n. Okay, so n is the number of rounds divided by the suboptimality gap. Okay, so so the proof is going. So we're not going to give the proof in this lecture, but you can read about it in the lecture notes. Okay, so we just want to note over here that log. Okay, so the only dependence on n here is in the log term, and this is pretty remarkable because the log function grows extremely slowly. So over a long time horizon, this means that we always pull the best arm, right? And we very, very seldom pull suboptimal arms. Okay, so this is a huge advantage for the UCB algorithm. Okay, and so I just want to give some intuition for how the proof works. Okay, so it's actually very intuitive. Okay, so it's sort of based on the following observation. Okay, so we only incur some additional regrets at every round if we pick a suboptimal arm during that round. And so we need to examine when that happens. Okay, so whenever we pull the suboptimal arm, okay, let's call it A prime, then one of the following has to be true. Okay, so first thing that can go wrong is that the upper confidence bound for the best arm, okay, A star, is somehow smaller than the true mean of the best arm. Alternatively, it could be the case that UCB for this other arm, A prime, is bigger than the best arm, or the true mean for the best arm. Okay, so when does the first condition happen? Okay, so first condition is saying that our confidence interval for the best, for the mean of the best arm, somehow does not actually include that mean, that value, I mean the true value. Okay, and so this is going to be highly unlikely because of our concentration inequalities. And then for the second condition, when does this hold? Okay, so this is all saying that even though A prime is suboptimal, my optimistic guess of it is bigger than the mean of the true arm. But the more times you pull A prime, okay, the larger the denominator inside the exploration bonus. And so this UCB, the bonus is quickly going to shrink. And so condition 2 is only going to hold for a few rounds before it stops being the case. Okay, so in total, this in sum, because this holds for every suboptimal arm A prime, this is going to allow us to control the number of times that we pull each suboptimal arm, right? And that's going to give us this regret bound that we have up here. Okay, so this is a regret bound for UCB. Okay, we can also get regret bounds for explode and commit. Okay, so let me state what that bound is, and then we can do a comparison. Okay, so recall what explode and commit does. Okay, so it separates exploration and exploitation into two phases. In the first phase, we pull every arm m times, and then thereafter, we look at what arm has the highest observed mean rewards, and then we keep pulling that arm henceforth. And the second phase, which is all about exploitation. Okay, so we call that m is equal to number of times each arm is pulled in the first phase. And so the theorem is as follows. So regret for ETC satisfies Rn is less than m times the sum from 1 to k of the suboptimality gaps for each arm plus n minus m times k times the sum from 1 to k of, again, the gap times this exponential term. Okay, so first, okay, so let's discuss this regret bound. So the first thing to observe is that the dependence on n over here is linear. Okay, so n occurs by itself. And so as the time horizon becomes longer and longer, the regret is going to be some constant term, some term over here times n. Okay, so the regret is going to grow linearly in the time horizon. Okay, and that's going to be much worse than the logarithmic regret that we got from the UCB algorithm. Okay, so this really shows that UCB is better than explode and commit. Okay, and then the next point is what this bound means. Okay, so this bound is actually very intuitive. Okay, so you're going to do a derivation of this on the homework, but for a simple case, which is when there are only two arms. Okay, so there's the best arm and then the other arm. Okay, but if you look at the two terms here, it's sort of intuitive where they come from. So the first term, this one over here, is the price that you pay in the exploration phase, right? Because we need to pull every arm m times. Every time you pull this suboptimal arm, we incur the additional regret of the suboptimality gap, delta A. Okay, and so now this means that the price that we pay for every arm is m rounds times delta A. And then we have to sum this over all the k different arms. All right, so this is the price paid in the exploration phase. And then what happens in the second term is that for every arm, okay, we put the m times. Then in the second phase, the only time that arm can contribute to the regret is if we mistake that arm as the optimal arm. Okay, and what's the probability of mistaking arm A for being the optimal arm? Okay, that's simply going to be equal to this exponential term here. Okay, so this is probability of mistaking arm A as the optimal arm. And if that happens, okay, if we mistake arm A as the optimal arm, then for every round, the price that we pay is going to be the suboptimality gap. Okay, so it's going to be delta A. And because the number of rounds left is n times n minus k, so n times n minus m times k, then the price that we pay is n minus m times k times delta A. Okay, so we have to take this price and multiply it by the probability of the bad events, and that gives us the price for one arm. And now this could happen for any arm, so we have to sum over all the k arms. All right, and this gives us the formula for the regret bound for ETC. So this is what happens in ETC for some fixed value of m. Okay, so some fixed value for the length of the exploration phase. And so if we were given some additional information, so if we could pick m depending on the suboptimality gap delta A and the time horizon n, then we can actually do better. Okay, so here's a remark or note. If we set m to be equal to 4 times log n divided by delta min squared, where delta min is going to be the minimum over all the arms that are not the optimal arm of delta sub A. Then the regret that we get is less than 4 times log n divided by delta min squared plus 1 times the sum over the suboptimal arms of delta sub A. Okay, and again, we see over here that the regret that we have is logarithmic and n. Okay, so this might seem to suggest that ETC might be just as good as UCB. Okay, but here we have cheated because we have used this unknown knowledge about the time horizon n, as well as the minimum suboptimality gap in order to set m. Okay, but in practice, we don't actually know these two quantities. Okay, so you might actually know the time horizon, but we will never know what this suboptimality gap is. We are now going to consider a third algorithm for tackling the stochastic multi-armed bandits problem. This algorithm is called Thompson sampling, and it is going to be a Bayesian algorithm in contrast to ETC and UCB, which are both frequentist algorithms. Being Bayesian means that Thompson sampling can incorporate prior information. Okay, so this is some additional information that you have to feed into the algorithm. And then, using the prior information, as well as the data observed from pooling the arms and different rounds, we can construct some posterior distributions, and then we're going to make use of posterior distributions for the rewards, for the mean rewards for each arm to make decisions. All right. So this is both somewhat similar and also different from making use of confidence intervals to make decisions, which is how the UCP algorithm works. Okay, so now for some history. So this algorithm, Thompson sampling, or TS for short, was actually introduced in all the way back in 1933. So in the previous video about the history of Bandit problems, 1933 was also the year in which the Bandit's problem framework was introduced by Thompson. And in fact, he proposed this algorithm, Thompson sampling, to try to address it. This means that, this means that Thompson sampling was probably the first Bandit's algorithm. But despite being the first Bandit's algorithm, it turns out to be a really good algorithm, and it's still being used today, and it is still the top of research and still being used today, both in academic circles as well as in industry. All right, and so to tell you how this algorithm works, I need to first set up some notation. Okay, so because we need to compute posteriors, we need to be very careful about what data we are conditioning on. And so we need to add some new notation to the arsenal that we already have. So previously, so we need some new notation for rewards. Previously, we had the sequence x1, x2 to xn. Each xi is the reward that we observe in round I, but it's not clear which arm the reward comes from, at least from this notation. So to make that clear, we're going to introduce this n by k matrix of potential outcomes, of potential rewards. Okay, so instead of looking just at the actual rewards that are observed, we're going to have this theoretical construct of rewards that you could possibly have observed. Okay, so they're going to be k columns. So let's assume that k is equal to 5 for simplicity. All right, so let's do it this way. 1, 2, 3, 4, 5. Okay, so I didn't actually need this part here. And then, so one column for each of each arm. And then I'm going to have n rows. And then so on and so forth. And now for each column, the entries in the column x1, 1, x2, 1, x3, 1, and so forth. Okay, so all of these are going to be drawn according to the distribution for rewards for arm 1. And then likewise, for the second column, okay, so all the entries in this column are going to be drawn from the distribution of rewards for arm 2, and then so on and so forth. Okay, so I'm just going to fill in a few more of these entries. Okay, so formally speaking, we want xij to be drawn according to the distribution, the reward distribution for arm j. All right, so now what happens when we run our Bandit's algorithm and observe certain rewards? Okay, so we start off by not observing any entry in this n by k matrix. And then in round 1, if we pull 5, for instance, okay, we're going to review this entry. And now Okay, so we're going to review this entry. And so the first observed reward is going to be x15. And now in the second round, we're going to make another decision. Okay, so we have to choose which arm to pull. So say I pull arm 3, then I'm going to review this entry. Okay, in the third round, maybe I pull 5 again. I see this entry. And then in the fourth round, I decide to pull the first arm, for instance, and then I see this entry. Okay, so at every round, the reward that you see is going to be the first entry in the column for that arm that has yet to be reviewed thus far. Okay, and so mathematically, the rule is that in round T, the reward x sub t that we observe is equal to x sub t sub at. Let me do it this way. T sub ATA for A is equal to A sub T. Okay, so in other words, if the arm that we choose in round A, in round T is equal to A, then we look for the eighth column here. So A is equal to, say, for instance, A is equal to 4. And then we go down and we see which entry have we not seen so far, and then we choose to reveal it. Okay, so the index of the row that is the first entry that has not been reviewed is simply going to be this capital T sub A of letter T. Okay, so if you think for a moment, you see why this is true. All right, so this is going to give us some convenient notation in order to write our posterior. Okay, so now before we start, okay, to set up the Thompson sampling algorithm, we first need to give it some inputs. So we need to input the prior, pi A for each arm. And more precisely, this is going to be a prior for each arm's true mean reward mu A. And then we also need a likelihood, which would be distribution of xia given mu A. Here we need one of these for each of the arms. And now we're going to define the posterior. For mu A and round T is going to be P sub AT. Okay, and so as a posterior, we need to condition on all of the data we observed so far. Okay, so we usually assume that all the means for the different arms are independent. Okay, so we just need to condition on the rewards that we observe for that arm, and this is going to be x1 sub A to x t sub A t A. Okay, and I think, let me see. Yeah, so there's a slight problem indexing here. Okay, so in round T, if we have not yet made a decision, then the information we have up to that point is the information that we have up to around t-1. Okay, so this is the posterior. And now we can set the algorithm. Okay, so in round T, we're going to select an arm as follows. Okay, so there are going to be 2 steps. So first, we need to draw a posterior sample, which we're going to denote mu sub AT from each of the arms. And then we're going to choose the arm that has the largest sample. i.e., you're going to set A sub t to be equal to the upper max over the arms of mu sub AT. Okay, so in other words, the probability that we choose arm A for each A is the probability that that arm A, is the largest arm under the posterior. And this is the posterior with respect to all of the data that we have observed so far. Okay, so again, it's pretty intuitive what's happening. Okay, so if we have, if the rewards for arm A have been, that we observed so far is high, this would mean that the posterior mu sub A, P sub AT is sort of going to have a larger mean. And so the probability that it is going to have the largest value under a posterior sample is going to be higher. All right, so we're more likely to choose that arm. Okay, so the logic is pretty clear, but maybe this still sort of has a somewhat black boxy type of flavor, because posterior distributions might really be because now we're talking about this in the abstract, and before we supply some more precise description of what the prior and likelihood is, it's not so easy to think about posterior distributions. Okay, nonetheless, we can assert the following theorem. Okay, so this is a regret bound for Thompson sampling. Okay, so under some conditions, which I'm not going to write down, the regret of Thompson sampling satisfies this limiting behavior, okay, where if I take the ratio between the regret and log n and take a limit, okay, so this is going to be less than or equal to the sum over all the arms with the suboptimal of 2 divided by this suboptimality gap. Okay, so this is essentially saying that the regret growth for Thompson sampling is logarithmic in the time horizon n, right? And this is a property that is shared by UCB. All right, and this is sort of unsurprising because for large samples, the effect of the prior sort of gets washed out by the data that we observed. Okay, so you probably have seen this when we worked with Bayesian sampling and the unit that we had in this class. And so here, if n becomes large, the prior doesn't actually matter anymore. And so when you work with the posterior distributions, they tend to just resemble frequentist confidence intervals. Okay, so making decisions based on these posterior distributions is going to be pretty similar to making decisions based on frequentist confidence intervals. Okay, so Thompson sampling for large sample sizes should behave very similarly to UCB. I now want to do a quick comparison of Thompson sampling and UCB using the results of a simulation. In this simulation, we have a fixed bandwidth environment that we use for each of the algorithms. And then for each algorithm, we're going to make use of a time horizon of 1,000 rounds. And we're going to run the algorithm over this period of time. And then we're going to do this 20 times in total and average out the pseudo regret over this time to get a curve of regret with respect to time. Okay. And so we did this for 4 different algorithms. We did this for UCB, Thompson sampling with a good prior, Thompson sampling with a bad prior, and Thompson sampling with a prior that has the same mean for every single arm. So let me say a few more words about what a good prior is and what the bad prior is. So the ground truth is going to be the case that my arms, so I believe I have 10 arms. Okay, so each of the arms is going to have some ground truth mean. And I think we asserted that the means are going to be ascending. So arm 1 is going to have the smallest mean, arm 2 is going to have the second smallest, and so on and so forth. So having a good prior means that we assume that for our prior pi 1, pi 2, and pi 3, and so forth, the mean for pi 1 is smaller than the mean for pi 2, and which is smaller than the mean for pi 3, and so on and so forth. Okay, so the prior information actually reflects what is happening in reality. So that's a good prior. A bad prior is when this ordering is flipped. Okay, so the mean for pi 1 is the biggest, the mean for pi 2 is the second biggest, and so on and so forth. Okay, so it's the reverse of what actually is the ground truth. And for when we run Thompson sampling with the same prior, this means that the mean for each of these priors is exactly the same. And so this plot that you are seeing right now is showing the results of regret over time for each of these algorithms. Okay, so the best performing algorithm is Thompson sampling with a good prior. And then this is followed by Thompson sampling with the same prior over all the arms, followed by UCB. And then finally, we have Thompson sampling with a bad prior. Okay, so the simulation is sort of showing you that the performance of UCB is sort of intermediate between Thompson sampling when we have a good prior and Thompson sampling when we have a bad prior. All right, so in other words, if we have some good information about reality and we incorporate it into Thompson sampling, then this is going to help you. But if you incorporate the wrong information, that might actually hurt you. Okay, but it's sort of curious over here that if you don't include any information, right? So you have the same mean for the prior for every arm, then Thompson sampling seems to be doing better than UCB. Okay, so this does not actually mean that UCB is a worse algorithm overall. Okay, so there are a few reasons for this. One reason over here is that this is just for one simulation. Okay, so this is one regime of arm distributions, number of rounds, number of arms, etc. Okay, so for other configurations, there might be some different behavior. And also the algorithm, the UCB algorithm that we introduced in this class and that we're using over here is sort of like so it's pretty good, but it's not actually the best version of UCB. So over the last few years, people have improved upon UCB and tweaked it a little bit to make it slightly more complicated, but also a little bit better. Okay, and so the regret of those versions of UCB is actually smaller than what we see over here. Okay, so the main takeaway is that UCB and Thompson sampling are both pretty comparable. And the performance of Thompson sampling really depends on the quality of the prior that we use. Okay. One thing to note over here is that regret, so we're sort of comparing all of these algorithms using the notion of regret. Regret is fundamentally a frequentist notion. Okay, so for regret, we assume some ground truth, right? So we assume some true reward distributions for each arm, and then we measure the quality of our decisions with respect to this ground truth. Okay, so despite Thompson sampling being a Bayesian algorithm, we can still analyze it in the frequentist framework, which is what we did over here. We see that Thompson sampling still has good frequentist properties, meaning having small regrets. Okay, so this turns out to be a feature of many Bayesian algorithms, okay, which is a good thing. So this is sort of it's a partial marriage between the frequentist and Bayesian worlds. In the last part of today's lecture, I want to take a step back and consider bandit problems more generally. So far in this course, we've only considered one type of bandit problem, which is that of stochastic multi-armed bandits. And it actually turns out that there are many other types of bandit problems with different assumptions and different environments. Okay, so here I want to introduce some of these other problems to you. And I just want to say that none of this is going to be tested on your midterm or in the homework, but I think this is very good to know. Okay, so firstly, to know what's out there. And secondly, when you think about modeling, okay, so we're not just learning bandits in the abstract. We want to learn about bandits so we can use it as a framework for how to do decision making in certain situations. Okay, so whenever you try to model some phenomenon using the bandits framework and adopt bandit algorithms, you're implicitly making some assumptions. And we want to know whether those are good assumptions or not. Okay, and having a sense of what other bandit problem frameworks there are, it's going to really help us make these very crucial and yet tricky decisions about modeling with bandit frameworks. Okay, so here goes. Okay, so the first other type of bandit problem is called an adversarial bandit problem, or just adversarial bandits. And this is where we assume that the distribution of rewards is not stochastic, okay, which was the assumption for stochastic multi-armed bandits, but instead it can be anything, it can be arbitrary. Okay, so this means that whenever after we make a decision, the reward that we get can be chosen in the worst possible way by some adversary. Okay, and this seems to make this problem intractable, but actually that's not the case. Okay, so when will this ever happen? When will this ever be a good model of reality? Okay, so I would say that this is perhaps going to be more appropriate whenever your environment comprises other people or other agents who are also trying to optimize for themselves. Okay, so in that case, okay, when you're interacting with other agents, they're going to choose behaviors or actions that are going to benefit them. Okay, so they're going to adapt to your decisions in a way that benefits them and disadvantages you. All right, so this has a lot to do with game theory, and this is more than just superficial. There's actually a deep connection between these two topics. Okay, and then moving on from adversarial bandits and returning a little bit to the stochastic world, here we have this topic called contextual bandits. And in contextual bandits, here we put on some additional assumptions into our environment, and what we do is that we assume that for every round, in each round T, the learner receives some side information. The side information is called a context, and it is usually denoted with CT. And we can use CT to make a better decision, because CT is going to be correlated to what the rewards are in round T. Okay, so this is because we usually model the reward xt at round T to be equal to some function of the context and the arm that you choose in that round plus some mean zero noise term. Okay, so CT, knowing CT is going to give you some additional information for what the optimal arm choice is in that round. Okay, and in different rounds, there could be different optimal arm choices because of this formulation. Okay, so when is this appropriate? Okay, so if you recall the restaurant example where we're trying to, to eat the best food or the food that gives us the most enjoyment, then it makes sense that we're going to, at any moment in time, we're going to have some kind of craving, right? And these cravings are going to influence which restaurants we like more in that moment. Okay, so say I have some craving for fried chicken at the moment, then I'm going to be pretty happy if I go to some place like Wendy's, right? And this is not to say that Wendy's is objectively a good restaurant, but it just so happens that at that moment in time, because of my craving, I'm going to get more enjoyment from going to Wendy's than usual. Okay, so this is the notion of a contextual bandit. And then we also have versions of bandits called non-stationary bandits. And this is where the reward distributions for each arm is allowed to change with time. Okay, and so this would be a better model for dynamic environments, okay, where your environment keeps changing. Okay, so like in the restaurant example, the quality of restaurants is not going to be fixed. Okay, it's going to vary over time, where so it's going to depend on whether the management stays the same or changes, whether the chefs in the kitchen are the same or not. Okay, maybe it depends a bit on you as well. Okay, and then so here are three different types of other bandit problems. So there are actually a lot more. So in the notes I also introduced a few more of these, but I'm going to refer you to the notes for further reading. Okay, and I just want to say that so these are the other kinds of bandit problems, and naturally they're going to have their own types of algorithms that are catered to these different situations. Okay, but the algorithms are going to be different, but they're going to share a lot of properties to those that we already seen, namely UCB and Thompson sampling. Okay, so the other algorithms for these situations are going to be pretty similar, and they might even use UCB and Thompson sampling as building bricks in order to construct slightly more complicated algorithms. So now I want to end with a discussion about model checking. Okay, so as I said, we don't want to consider bandits as an abstract academic subject. Okay, so the whole point of studying bandits is that we can use it to try to model the world. Okay, so we always have to ask whether, so the important question is to ask whether the environment that we assume a good model of reality okay, and previously we really discussed why viewing the restaurant problem as a multi-arm bandit problem might have some issues, right? So there were issues with stationarity, right? So the quality of each restaurant is not is not static, but changes with time, right? So we might want to incorporate some, allow the reward distributions to be non-stationary. And then also we have some access to context, right? So this can be our cravings, it can also be other factors, temporal factors, say who we are eating with at the moment. Okay, maybe we have we're eating with a friend who prefers some certain type of foods. Okay, and another assumption that we were making is that the rewards are independent of each other, but this actually may not be the case, right? Because restaurants that all have the same cuisine, okay, so the rewards for those restaurants are going to be, that we get is going to be pretty similar, right? Because if we dislike some dim sum restaurant, for instance, then it's more likely that we're going to dislike other dim sum restaurants, because it just could be this, could be the case that we don't like this type of foods. Okay, so what can we do whenever, say, we start off with a multi-armed bandits framework and we see that the assumptions are not really holding? Then we might want to expand the model to account for this. Okay, so we can expand the model and in the restaurant case, this could be that now we allow the reward distributions to be non-stationary, and then we also allow for there to be context. Okay, but when we expand the model, okay, this sort of reduces bias in some sense, but then we have to account for additional variance, right? Because we have this bias variance trade-off. Okay, and what we mean in this case, in the bandits case, is that if we have a larger model, right? So there's more to learn, then this will mean that we are going to require more samples, right? So a longer time horizon before we converge onto the optimal policy, right? Okay, so if the reward distributions are non-stationary, then we're going to have to keep learning about it. Okay, so we cannot settle as would be the case in UCB. Okay, so we definitely have to take into account this. Okay, so when we model, right, we have to, there's going to be this trade-off. So on the one hand, by having a more flexible model, we can reduce bias, but it's going to increase variance. Okay. So these are important issues that we have to keep in mind. Okay, so again, in the notes, there's a extended discussion about this, and I'm going to refer you to the notes to read more about this. Okay, so I just want to conclude by saying that this problem of bandits is very important for many reasons. Okay, so on the one hand, it's a good model for many real-world problems, and on the other hand, it's good as a pedagogical and academic topic. Okay, because this really reveals the heart of this exploitation trade-off, which is just a fundamental issue in online learning and online decision making in general.